Hello everyone, my name is Simin Chen. Today I would introduce DENAS. DENAS is a tool that can generate human understandable rules from neural networks. This work is cooperated with Soroush, Sampath, Xiaodi, and advised by Professor Liu and Professor Yang. Today, deep learning is pervasive in our daily lives. Researchers have applied deep learning techniques for automatic testing, code analysis, and malware detection. Okay, let's first review how deep neural networks make decisions. Deep neural networks apply nonlinear activation function to simulate the neurons in the human brain. The combination of thousands of the nonlinear neurons in the neural network enable it to make complex decisions. Let's first see how nonlinear activation function could improve the performance of neural networks through a simple example. Let's first see a linear model. In this linear model, the decision boundary is very clear. However, this linear model may suffer from the problem of bad performance. In our case, there are 3 false negative and 1 false positive. When we apply the nonlinear activation function, the decision boundary would be more complex and the performance of this nonlinear model would improve much. The decision-making of when applied this nonlinear activation function, the decision-making would be complex to be understood. Let's compare with the traditional software. For traditional software, the decision-making is based on the linear logical rules encoded in the source code, which is easy to be understood. But for deep neural networks, the decision-making is based on matrix computation and the nonlinear activation function. The combination of nonlinear activation function and the matrix computation would cause the complex decision boundary of neural networks, which is hard to be understood by the human beings. Due to these concerns, we want to combine the best of the rule-based software and the deep neural networks. In this work, we propose DENAS. Let's first review how to build a rule-based system. To build a rule-based system, it requires a set of rules. To get such a set of rules, it requires the domain-specific experts to analyze a large dataset. Based on their knowledge, they would produce such a set of rules. However, this phase is usually quite expensive, which requires much manual efforts. We want to bridge this gap by providing DENAS. DENAS could extract knowledge from a well-trained neural networks and produce a set of human understandable rules. After verification, this set of rules could be used to update the original neural networks. Before we introduce our design, let's introduce what is a rule. A rule consists of the if statement and the then statement. Let's use Android malware classification as an example. For Android malware classification, the if statement is the sensitive permission the app requires, and the then statement is to decide whether this app is a malware or not. In this example, the sensitive permission is send SMS, and the label is the malware. Okay, next I will introduce why the existing work cannot achieve the rule extraction. The existing work can be categorized as local explanation approach and global explanation approach. For local explanation approach like lemma, CM, IG, and gradient. The mechanism of local explanation approach is to identify the features for one specific input which have a highest gradient to the final results. For example, give an image, they would identify the pixel which impact most to the final results. However, this type of approach solves the problem of where to explain. In other words, there are so many of data instances, they didn't know how to select the input to give explanation, which means this type of approach lacks representativeness. For another type of approach, global explanation approach, like tree regression and the DTX chart. This type of approach is the working mechanism of this type of approach is to build a human interpretable model to fit the input and the output of the neural networks, as shown in this figure. However, to train a human interpretable substitute model, they need to select a set of random data to train this model. The randomness in selecting the data to train the substitute model would cause this type of approach unstable. In other words, the different random sample data would cause the generated rules different, which means this type of approach unreliable. In our case, if we choose this dataset, we would get the model. We would get two models as shown in this example. To address this challenge, our goal is to provide a stable and a global knowledge extraction approach. Before we consider the complex neural networks, let's consider linear model. This is a simple case. Let's consider this simple case. Which feature might dominate the decision boundary of this model? In our case, the feature x1 would dominate the decision boundary. Why? This is because the weight of the feature 1 is significantly larger than the others. Then the problem is how to convert the nonlinear deep neural networks into a linear model. To achieve this goal, we have three intuitions. First, the source of the nonlinearity of deep neural networks is the identification function, and we can use the piecewise line to approximate the identification function. For example, ReLU, which is a widely used identification function. We can approximate ReLU with two lines, namely y equals 0 and y equals x. For each line, there are two parameters as the scope and the bias. Even we can approximate the nonlinear identification function with piecewise line. Another problem is, for different input case, the parameter of the identification coefficients might be different. In our case, it's the scope and the bias. Then, how to choose the global property of the nonlinear identification function to represent these parameters? Our intuition is the mean value of the identification coefficients is a global property. We can use that to represent a distribution of data. As shown in this figure, we can use the mean value of fx to represent the different value distribution of the fx from A to B. Then, even we can know the problem is how to calculate the mean value of identification coefficients. We have mathematically proved that the mean value of identification coefficients could be calculated through the activation probability, and the activation probability is a stable and a global property of neural networks, which could be estimated through Monte Carlo sampling. Let's show an example. In this example, we randomly choose 3 neurons in a neural network, and we plot how the activation probability would change as the randomly sample number n increases. The experiment results show as n increases, the activation probability converges. And we have mathematically proved that n equals 1000 is sufficient to get a stable activation probability. Okay, based on these 3 intuitions, we can transfer the nonlinear decision boundary of the neural networks into a linear one step by step. Then I will introduce the details of our design. DENAS is an iterative approach which contains 3 main parts. For the 3 parts, DENAS estimates the activation probability based on random sampling. After that, DENAS approximates the decision boundary based on the activation probability. After that, DENAS chooses the feature value and use the feature value to update the current rule. DENAS iteratively performs the 3 basic steps until the rule satisfies the end conditions. Okay, we invert DENAS from perspective representativeness, stability, and accuracy. Or we invert DENAS for 3 different tasks, namely binary code analysis. This is to decide the byte in a binary code is a function entry or not. The input is a sequential binary, and the output is to identify each byte is a function entry or not. And the second, PDF malware detection. The input is a PDF malware instance, and the output is to decide whether the PDF is malware or not. And Android malware detection, similar with the PDF malware detection. We consider 5 baselines, namely lemma, gradient, IG, deep Taylor, and DT extract. We first invert the representativeness of DENAS. We use the coverage as a metric. We define rule coverage is the percentage of the data that matches the rule. The experiment results as shown in this figure. For simple tasks like PDF malware detection, DENAS performs similar with the baseline. But for the other 2 tasks, DENAS, the red line, outperforms the baseline a big margin. For stability evaluation, we random sample the dataset 1 and dataset 2 and apply DENAS to get the rule set 1 and rule set 2. We define stability as this equation. The stability result as shown in this table. The first row is the result for DENAS. The result 1 means DENAS could produce stable results even with multiple runs. Finally, we invert DENAS for the perspective accuracy. We follow the existing work lemma to design augmentation experiment and a deduction experiment. Let's use an example to explain these 2 experiments. Give an original input, DENAS would first identify a rule this input satisfies. Then for augmentation experiment, DENAS create an input which only keeps the feature value in this rule. This is designed for augmentation experiment. For deduction experiment, DENAS would remove the feature value from the original input and create a new input for deduction, like this. For augmentation experiment and deduction experiment, we want to see the new generated input whether would have the same prediction result with the original one, which means the identified rules can represent the decision-making of the neural networks. For augmentation experiment, the results are shown in this figure. The red curve is the result for DENAS. The results show DENAS could perform best on binary analysis and PDF malware detection, and similar with Deep Tailor on Android malware detection. For deduction experiments, the results show DENAS achieved the best performance on 3 tasks. Before the performance evaluation, we also used 2 case studies to show why DENAS is useful, namely extracting the new knowledge from neural networks and fixing natural neural networks faults. As shown in this table, the different color law represent the different year we correct Android app for erosion. And the colon train means the year we correct app to train the neural networks. And the colon row represents the rows we identified from DENAS. And the colon appeal represent the app instance satisfy this rule first appeal. Case 1 to 5 shows the new rules. The new rules means the app satisfy this rule doesn't appear in the training dataset of the neural networks, but appear in the future, which means we can apply DENAS to extract new knowledge from our trained neural networks as a malware signature to detect zero-day malware. And the case 6 to 8 shows the faulty rules. Faulty rules means the rules is consistent with the decision-making of the neural networks, but are contrary to the ground truth, which means these rules are the position where the neural networks make mistakes. We'll learn how we leverage this point to debugging neural networks. As shown in this figure, the black points are the misclassified app. We first apply DENAS to find the faulty rules for this misclassified app, and then we generate some points to augmentate the original dataset to retrain the neural networks. After retraining, we want to modify the decision boundary to make the misclassified app to be correctly classified and doesn't harm the overall performance of the neural networks. The results are shown in this table. We randomly chose 4 rules for evaluation, and we set the KP to 20 and 14 for evaluation. KP is the number of the augmentation data number. The experiment results show after debugging, the incorrect case decreases while the overall performance keeps almost the same. Our conclusion is understanding the decision-making of deep neural networks is very important, and the identification probability is a stable and a global property of deep neural networks, which could help to understand the decision-making of deep neural networks. Thank you.